Thank you, colleagues. It's indeed an honor and a pleasure to be with the who's who of robotics here. And thank you to Sami and his team for the invitation. It's a huge effort to set up a center like this. It's a beginning of a journey, and I wish you all success. I'm going to try and structure the talk slightly differently because all my colleagues have already talked about all the cool stuff, so there's nothing left to talk about in terms of the science. So what I'm going to do is try and go at it from a point of view of what are the cool things that we need to use robots for, and then try to look at some of the science that we've been doing to try and address that. So I don't need to impress upon this community that robotics is now going beyond the classical ways of usage. So all the way from the traditional manufacturing stuff to now even looking at security in food security and autonomous driving in smart cities. But if you look at the trend, so traditionally, we've looked at robots that are teleoperated, either programmed to do things and repeat things in a particular way. Recently, there's been an emphasis on going towards significant more autonomy into the system. But I personally believe that the challenge in the next sort of 10 to 15 years is not going to be waiting for fully autonomous robots, but somewhere in between, where we need to be able to seamlessly transfer between a fully teleoperated system and a fully autonomous system, and somewhere in between, even within a single task. So there are significant challenges to address in the area of shared autonomy. So what is different, and many of you have already addressed this, the classical ways of doing robotics has reached a limit because of many of these challenges. So if you look across the domains, so these are roughly the domains that Edinburgh Centre for Robotics works on, there are significant, if we wait for full autonomy to work in these systems, we're going to wait a long time. So to be able to address these things, we've been looking at several domains. So what I'm going to do is to give you examples of 3.5 projects, so I have time for 3, I think, and tell you a little bit about the science underlying that. So the first one is what I call shared autonomy for remote ops or remote operations. So you can imagine scenarios where you want to send a robot into a fairly dangerous radioactive setting. The whole point is you want to be away from the line of sight. You need to have scenarios where it works without reliable communication. That's on the right-hand side is a console that the robot is seeing. It builds a live state estimation of the world, and it does most of its actions autonomously. It decides for itself the path planning bit, the figuring out which hand to use to clear debris, but the human is still in the loop trying to tell it which object it needs to grasp and where it needs to be put in. So there is still a level of human in the loop control that's happening in those scenarios. So to be able to make something like that happen, what are the core scientific technologies that we need to solve? So Dieter already mentioned a lot of things today with respect to the sensing. So you want to go from pretty raw sensing information. This is the view of the world through a robot's eye. You want to go from something like this to something like this, where we want real-time tracking. We want to be able to do, in this case, this is probabilistic model-based tracking. And you want to do this under clutter. You want to do this in the presence of significant noise. And you also want to do this under motion, because you cannot guarantee that a camera is going to be still when it's on a robot's head. So doing all of these things robustly, not taking ages, but doing this in real time so that you're able to adjust your actions on the fly is a big challenge. So online real-time perception is a big challenge, and we are doing some bits of work towards addressing this. So we have specifically looked at a particular program of motion planning, which combines or really actually separates the issue of motion planning, the problem of specification of the problem, and the planning scene. So I encourage some of the young researchers here to go download this, try this out, because what this framework enables is to really try many sort of nonlinear motion planning algorithms from different communities, but set up common motion planning problems and evaluate this across domains. So this has been quite beneficial for us for this domain. And of course, using these concepts, we've been doing many projects across domains. Specifically, I want to point out the one on the top right, bottom right, yeah. So if you go to London now, there's a big hole, there's a big hole underneath London, which is a Crossrail project. So we're working with some of the companies there to try and take some of those heavy machineries and make it idiot-proof, essentially doing this concept of shared autonomy, using real-time sensor data. So the second project I want to focus on is something slightly more exotic in terms of the challenges. It is about trying to, it's called the Orca Hub. It stands for Offshore Robotics for Certification of Assets. And it's about taking multimodal robots, robots that are topside, that are underwater, that are drones, and combining them to do things like asset inspection. And of course, in our lab, we do build some robots, but a lot of our robots come from great labs like the ETH. This is the animal from ETH, so we use those platforms to do real-time control, real-time motion planning, and robust motion planning with these structures. So again, if you look at the science underlying what needs to happen in such complex environments to enable this. So one of the concepts we've been focusing on is bridging the gap between robot speak and human speak. So for that, we have found the concept of topology, a way of representing motions, a way of representing relationship between objects and targets as very useful. So let me start by giving you a very simple example. To reach into a box, you can specify this target in n number of different ways. But if you use the concept of topology and specify targets by saying you want to move the topology from something which is outside the box to inside the box, then there are certain advantages. So for example, to reach into this box, you can do this in n number of ways. But if the box moves, then by using topological constructs, you're able to do very quick online remapping. And because of that, the concept of what is inside and outside moves with the box, and topological constructs help you do very fast replanning in this way. And this is just one simple example. There are other ways of representing abstract spaces like harmonic fields and relational tangent planes as clever representational ways for generalizing. So, of course, even if you have the best sensing and tracking, even if you have the best representation, the world is inherently uncertain. It's got noise in the world. So we have worked with various compliant actuation systems. You've already heard a lot of talks today, which focuses on variable impedance and variable compliance. And this is where I worked with Sami during his DLR days on working with looking at machine learning algorithms that are able to optimize variable stiffness trajectories. In other words, not just the kinematics and the dynamics, but also optimize the temporal evolution of stiffness profiles. So again, I don't want to put too many equations on the slide, but fundamentally speaking, it is using compliant actuators, using the classical ways of doing control, optimal control, so model-based objective functions, the optimal controller. The only difference is we have now used the variable impedance as an additional dimension in terms of the redundancy and solve that redundancy on the fly. So the way we do that is by using probabilistic inference as a way of solving these mechanisms. Why is this useful? It's useful because now you can work between abstractions. Remember, I said we can work with tangent planes or relational metrics or topological constructs. You need to be able to move between these constructs on the fly, and these graphical models and variational inference methods help you do that seamlessly. Great. So what are the kind of things that we have done with it? So we've used some work to optimize stiffness trajectories so this is now two-link variable impedance systems which can pump energy into the system, modulate stiffness optimally in order to create, in this case, maximize throwing performance. In this case, it is maximizing the distance thrown by pumping energy into the system. So what we've done here is we have optimized the scheduling of the stiffness properties using purely optimization techniques. And this is work at Sammy's place in DLR, where we tried to scale that up to a big system, the hand-arm system that again you've seen in some other labs. So algorithmically trying to optimize the stiffness profiles. Now we've been trying to take this principle and apply it to various series elastic actuators that we have in our labs. So for example, we now have the animal platform on which we are trying to, again, optimize stiffness profiles. Some of Antonio's students are visiting us, working on some of those platforms as well. Sorry, I'm going to turn off the volume. And more importantly, so the adjustment of the stiffness profiles help us do various tasks, like this is work that's coming out of Mike Mystery's group, who is also in Edinburgh, of trying to look at establishing contact, controlling wrenches, but doing this kind of distributed force impedance profiles in collaborative settings like this. So that is hugely important for scenarios where we want to interact with multiple robots and humans, still humans in the loop. So this is what I meant by shared autonomy. So sharing control and interfaces with robots. So we've recently also just started a very exciting new project. I saw a couple of people already talk about dyadic collaborations, dyadic manipulation systems. So this is some work that we've just started, and we've had some first results. It's going to be presented at Coral next week on not just doing trajectory optimization and optimization of dynamics, but also doing we are also adjusting contact locations and timings. So we are doing a continuous optimization of trajectory profiles as well as braking and making contact, and using this to not only use this as a way of collaborating, but also a way of, if you can predict user intentions, trying to use this in a collaborative fashion. So user intention prediction is still a very, very hard problem. But if we assume we are able to do that, we can optimize movements in collaborative settings. And why do we care about this? Because we want to work with things like, I think a bunch of our colleagues, including we have a project with LAS and CNRS with Airbus on collaborative manufacturing settings. Okay, so the other project I want to briefly mention is the work that we're doing with the Johnson Space Center using the NASA Valkyrie platform, it's an exciting platform, but it's also a difficult platform, a complex platform to work in. So we are a very small part of a big journey that NASA has. This has changed in the last few months. It's gone from going to Mars to pivoting to Moon as a partial. As a staging point, but still the scientific problems that need to address still remain. It's about getting robots like these. So this is doing fully autonomous. You'll see the sensing in a minute. It's doing footstep planning, placement, and adjustment of final pose and gait in order to manipulate the poses so that it is able to adjust its location in order to grasp in complex scenarios, in clutter. So what is important is the robot uses its live sensing to figure out the poses it needs to be, using these multiple supports to do this kind of navigation and manipulation. So again, fully onboard sensing. You'll see in a moment the work that we had to do in terms of getting the live sensor feed and the motion building, as well as the SLAM aspects. So again, sensor drift is a massive issue. So again, using work that a bunch of students, including Raluca, who works with Daniel, has been doing on motion building from live sensor data to do optimal planning. So you'll see also in a moment the live sensor feed for, in this case, end-step, look-ahead, footstep planning on these platforms. So it's quite a new experience for me trying to build full systems, all the way to sensor to perception. But that has taught us quite a few lessons in terms of where to go. So recently, we've also been looking at navigation in uneven terrain, on locomotion on uneven terrain, using again live sensor data. And again, I've cut short this video for time, but what typically happens is, depending upon the slope and the affordances for the footstep placement, it changes its gait and location position to grasp objects. Okay, so this is historical work. This is work from my PhD. This is work with Stefan and Jan and many others. But this is still so relevant because I still feel that all this work on data-driven learning of dynamics there's a lot to do in trying to use the existing models, but also trying to use live data-driven innovation to adjust the models that we learn. So in this case, here's an example of this work from my PhD times, where we did data-driven way of learning dynamics of the arms, but also learning task dynamics to learn to balance a pole. So to learning control policies on the fly using data-driven methods. And the way we use it now is, we put it inside the optimal control loop. So rather than taking analytical models, we put it in the optimal control loop to adjust the control loss. Okay, I don't think I have time for this, but come find me if you want this fun video of manipulation in null space to bringing all of these things together. So we also work in prosthetics. Again, I don't have the time to go much deeper into this. We work with upper limb prosthetics with type bionics, and lower limb prosthetics on looking at gait metrics for evaluation. But I want to finish by giving you a little bit more insight into the center that we run. And I think this may be perhaps a few hints for Sami to, there's some problems, there are some wonderful successes, but it's a challenge. So we want to address some of the global challenges by taking innovation from labs to market through 3 strands. Working with world-class assets, working with world-class PhD students, that's the skill bit, and working with government for clusters. So this is extremely important to make our research successful. So just blowing it up, assets, skills, and clusters. So what are these assets? What are the skill sets? We train our PhD students in robotics. We have about 15 odd PhD students working with companies very closely. It's called Center for Doctoral Training. We work with world-class equipment. The government has been massively supportive for that. And lastly, I want to finish by putting on another hat. So recently, I was given the massive privilege and opportunity to marry my 2 passions, machine learning and robotics. And I've just taken over as the co-program director of the Alan Turing Institute, which many of you have told that we should talk about AI and robotics together. And that's what we're trying to do in the Alan Turing Institute. So the take-home point is, we're looking at, in the Alan Turing Institute's RAS program, Robotics and Autonomous Systems program, we're looking at 3 key areas: scalable algorithms under constraints, methods for efficient multi-agent computations, and verifiable and robust explainable decisions for assets. And we definitely don't cover all of these things, but we're hoping that we have world-class experts who can come with us, work with us in this journey. To be able to do that, we've been doing things like setting up living labs in the newly opened Base Center. This is the bit. 10 days ago, we got 2 new floors of robotics facilities at Edinburgh. So please come and visit us, and I'm looking forward to further collaborations with Sami and the team. And I want to end by quoting one of my favorite authors. We tend to overestimate technology in the short term and underestimate technology in the long term. And that is indeed the case with robotics. So we have to cut down on the hype, look at the challenges, and make steps forward. So Godspeed to Sami, and the Munich School of Robotics, and I'm sure you'll do a great job. Thank you.